So I have previously said that any time you have a differential equation like this, where it's first order and the right-hand side only involves t, no x's, you can integrate to solve. So that sounds like, we totally know how to deal with all differential equations of this form. Well, sort of. One problem is that it's easier to say just integrate than to actually do it. Integrating is hard, right? Usually when you think of integrating, you think of anti-differentiating. So trying to find a function whose derivative is the integrand. So there you'd be thinking about indefinite integrals, and that's the kind of integral we did in the last examples we looked at. But that kind of integrating is pretty hard to do, actually. Most random functions that you write down are difficult to integrate. In fact, if you took the Math 3B course, you have seen firsthand how difficult it can be to do many integrals. And the only reason you can do the integrals in that course is because you only get to see the, quote, easy ones. Okay, so what do we do when we just don't know how to write down explicitly an antiderivative for the function over here? So let me just give you an example. Suppose you have this differential equation, x prime equals e to the minus t squared. What I have here is a function of t alone. So I should be able to integrate both sides, right? I should be able to say, okay, so then x of t equals the integral of e to the minus t squared dt, and then if I can just figure out what this integral is, then I can throw on a plus c, and there's my general solution. And then, if I've got some initial values, like an initial value problem like this, then I could plug in plug in 0 for t and set that equal to 2, and then try to solve for c. But I get stuck at the stage where I'm trying to figure out how to do this integral. So that shouldn't really stop me from at least being able to write down and talk about the solution. As it stands, it does stop me. So what I want to do in this video is show you how to remedy that situation. Even without being able to do the integral, you should still be able to talk about and write down both the general solution and particular solutions that satisfy initial conditions. We should be able to talk about them and write them down even when we cannot do the integral. So let's see if we can do this. So before we begin, we'll need some more precise way to talk about what's going on when we view integration as the opposite of differentiation. So what we need there is the fundamental theorem of calculus, one version of it. And this is the version we're going to use. If g of t is continuous, which pretty much means it's a nice function. Most of the differential equations you're going to get have at least that it's continuous. One way to think about it is when you're graphing the function, the graph doesn't have random breaks and jumps in it. If g of t is continuous, then if you were to integrate g from, say, 0, or from any number, let's say a, to t, then you would get a certain function of t whose derivative with respect to t is g of t. That is the fundamental theorem of calculus. Fundamental theorem of calculus. So the difference between what I'm writing here and what we have been using so far is that what we have here is a definite integral. Meaning, I'm not just talking about an antiderivative, but I'm talking about the area under the graph of a function with limits on the integral here. So the area under the graph running from a to t. So previously I would write things like integral gt dt, with no numbers here and here. And that just meant an antiderivative for g of t. That was not necessarily the area under the graph, right? Because you can't even see where to start and stop measuring the area. Now what I'm writing, let me just use this. Now what I'm writing, when I write things like this, where I do put numbers here and here, that actually is the area under the graph. Like if you were to graph g of t against t and get some graph, then A is somewhere and B is somewhere. And the area under here, that's what this number is. So here I'm saying do that, get that number, except measure from A out to t, and let t vary and then take a derivative with respect to t. Look at the rate of change as t varies of this area under the graph. The fundamental theorem of calculus says that when you take that derivative, you get back to g of t, actually. So let me give you an example just to show you, to make the notation make sense. Like, for example, if you're worried about why s's and t's are showing up in different places, I hope an example will make it clear. And if you're totally clear on what's going on, maybe skip ahead a little bit in the video. But here's an example. Let's say, say g of t is the function sine of t. Then the integral from a to t of g of s ds is the integral from a to t of sine of s ds is, well, the antiderivative of sine of s is negative cosine of s, or yeah, it's that. And then what we want to do is evaluate from s equals a to s equals t. And that would be negative cosine of t minus negative cosine of a. So if we compute the left-hand side in this example, if we compute the left-hand side of this equation in the example, we get d dt of the integral from a to t of sine s ds is the derivative with respect to t of this, which is let's see, so this is a constant when I take that derivative, and this is sine t. So you see how it worked? I'm not trying to prove it or anything, I'm just trying to demonstrate the idea and show you what is the role played by s in the notation and what is the role played by t. So s is like the dummy variable for the integral, and t is a bound here. So you can see that when we found an antiderivative for sine of s, we wrote it as a function of s in terms of s. And then t was one of the endpoints that we evaluated at. The other endpoint was some constant. All right, so remember this fact. And don't worry too much about continuous. That's just basically always going to be true for the kinds of things we write down. So pretty much remember this fact. A short way to remember it is to say if you integrate then differentiate, then you get back to the original function. But we need this like kind of more precise way of saying it. What exactly do you mean by integrate and then differentiate? We mean do a definite integral where one of the bounds is the variable with respect to which you're then going to differentiate. Then you get back to the original function. So how does this help us with the problem we were having with trying to solve a differential equation and just not knowing how to integrate and being stuck due to the integral? Well, let me write down that differential equation again. It was x prime equals e to the minus t squared. And actually it was an initial value problem that I wanted. X of 0 equals 2. So here's an initial value problem. And the problem I was talking about before is that we are stuck at first because we don't know how to integrate this. This is too hard to integrate. But what we can do is this. So apply the fundamental theorem of calculus to this function. So if I take derivative with respect to t of this definite integral, where the lower bound is anything, I'm going to choose something pretty soon, but let me just put an a here. And the upper bound is t, the thing that I'm taking the derivative with respect to. And then here I put this function. I can put any continuous function. This is an example of a continuous function. Oh, but sorry. Let me use an s here so that I don't confuse it with this t. The fundamental theorem of calculus says this will be e to the minus t squared. So when I'm trying to solve the differential equation, what am I doing? I'm looking for an x whose derivative is this, right? I'm looking for an x of t, a function of t, whose derivative is this. And here it is. Here is our x of t. Its derivative is this, is what's needed. So general solution to the differential equation is x of t equals integral from a to t of e to the minus s squared ds. And I don't know how to do this integral, but so what? I did write down the general solution. This integral is something. It evaluates to a number, right? That's because it's a definite integral. If it were indefinite, if I were writing this, then, I'm not really finished. I would have to, this doesn't evaluate to a number. But this evaluates to a number. You can, for any given t that you want to plug in, you can put it there, and then this will be a number. So I'm done with the general solution. And okay, well, usually with a general solution, we see this free parameter, right? For the general solution, we see a free parameter somewhere that parameterizes the family of solutions. Where's that? That's the a here. That's the free parameter. If I want, I can remove the a and put anything, just put a 0, and add a constant like c. And there's my there's another way of writing the general solution. So if you prefer to write it that way, then this is just some number. Anytime you plug in a t, this will be something. I don't know exactly how to get what number maybe, but you could get a computer to approximate it at least, right? I mean, an integral is just the area under a graph, so it's just a sum of a bunch of like rectangles where you make the rectangles get really thin. So you could make a computer compute this. So this is pretty good. All right, so here's our general solution. What about the particular solution? Let's satisfy the initial condition. So we need to demand that 2 be x of 0. That x of 0 is the integral from 0 to 0, plugging in 0 for t, of whatever, plus c. And what's the integral from 0 to 0 of something? 0. So c is just 2 here. So here's our particular solution. Meaning it's the solution to this entire initial value problem, to the entire thing that's boxed in. It's integral from 0 to t of e to the minus s squared ds plus 2. Great. And let me just, so here we kind of lucked out that when I plug in t equals 0, I get an integral from 0 to 0, so I didn't have to worry about this. But what if I did have to worry about it? Well, what I would suggest is you can choose this a however you want. So I just kind of randomly chose 0 here, and that's the reason I lucked out afterwards with the initial condition. So I would suggest choose that a cleverly. Let me show you an example where we have a different initial condition. Okay, same differential equation, but now suppose the initial condition is instead of x of 0 equals 2, let's do x of 7 equals 2. then from here I can use the fundamental theorem of calculus to get a general solution. And I can choose anything I want here for A. And if I choose something specific for A, then I can throw on the plus C, and I still am looking at a general solution. So that would be fine. And what should I choose for A? How about 7? How about I choose 7? So that makes it so that when I try to impose the initial condition, I get 2 equals x of 7 equals integral from 7 to 7 e to the minus s squared ds plus c equals 0 plus c. So c is 2 again. So if I just wanted x to be 2 at 7 rather than at 0 like in the previous example, I can just start the integral here at 7. So then my solution in the end is that. And yeah, let me just show you that this is something that a computer has no trouble figuring out. If we plug in any specific t, then this is just going to be the area under a graph, which is some number. So let me just show you that. Okay, so here's Mathematica, and you can just, so if I use n integrate, that should do numerical integration, which is, if you ask Mathematica to integrate, then it will attempt to find some antiderivative. But if you say n integrate, then it will just compute area under the curve, just adding up a bunch of rectangles or whatever the algorithm is that it uses. So let's say I want to know, let me pose a specific question. So here's a comment. What is x of 3? So let's make a kind of prediction. So x here is the state of some system that we're interested in, and we're told that our system evolves according to this law, that its rate of change, x prime, is always this. And we are told an initial condition, which is that at time 7, the state of the system is 2. Then we want to kind of do a back prediction. If we know that at time 7 the state of the system was 2, then what is the state of the system? Then what is the state of the system at time 3? So the answer is whatever the heck this evaluates to when t is 3. So that would be some integral plus 2. And here's how I could compute that integral. So let me first fill in the bounds of the integral. It's from t equals 7, from s equals 7. So the integral is d with a ds here. It's from s equals 7 to s equals t. To s equals 3, because I'm doing t equals 3 here. And the integrand is exponential of minus s squared. Oh, so it looks like it's that. 1.9998. Maybe it was actually supposed to be 2, and I'm seeing some numerical error. I don't know, but that's pretty close to the answer. So that's what x of 3 was, approximately. Just because it would be interesting, let's look at what you would get if you tried to just integrate instead of numerically integrate. So now I'm integrating this function with respect to s from s equals 7 to s equals 3. Look at that. So since this is a difficult thing to integrate, this is quite a hard integral to actually do, you might have expected that Mathematica would say, I can't do it. Or, I just don't know how to integrate this, or maybe it will compute forever and just never be finished. But no, it has something to say. something weird involving square root of pi and this ERF object. So, oops. Well, yeah, actually that's a good thing to do. Look at the help for ERF. So this is the error function, which is a really specific function having to do with the integral of e to the minus something squared. And you'll see this defined in your book in one example. And it's defined to be some integral. So Mathematica is just, it's not really computing an antiderivative here. Like, it's not really doing the integral. It's just giving you the integral in terms of another integral. So if you look at the definition of what this is, it's just another integral. So you'll have one homework problem where you need to work with this thing, and it's defined nicely in your book. For that homework problem, you will have to use the fundamental theorem of calculus to work with it, just because it is an integral, and while there's nothing wrong with that, you can't write it in any simpler way, using simpler functions like polynomials or whatever.